Okay, this was basically what we had done on Friday. Well, there were a couple of other mistakes in the calculations. For example, if you here on the top part, there is the I to the power 2L cancels minus 1 to the power L. But what we are left with is minus 1 from the first factor and I to the power 1 over I from the second factor. So that makes an I. We have the I squared, so that's the minus 1 on the left-hand side. Whereas on the right-hand side, we have just a factor of I. But that factor of I, we could have just absorbed in the definition of this phase, delta L, what we call a delta L. I mean, if you remember, we had a factor, a correction factor, which just turned out to be a phase. Now we can define that, we had defined it to be e to the power 2I delta L with a minus 1, but you can just define it with a minus I or an I. So it's just a shift in how you define that phase. And, well, if you make all those corrections, basically what you will end up having is that you will get just correcting some phases. That should be our result. And from this point on, so this is our differential scattering cross section. And from this one, we obtained that the total cross section was just the integral of f squared over all possible solid angles. And then we used orthogonality of the Legendre polynomials. And we obtained that this was equal to 4 pi over k squared, sum over L equal from 0 to infinity, 2L plus 1 sine squared delta L. This was our final result. And this delta L, sine delta L, this is just spherical harmonic, the L spherical harmonic of type J of Ka divided by, with a minus sign, JL Ka, no, this is plus I YL Ka, or let's say the absolute value is equal to this one. Now this is the corrected form. If you just fix all the signs and phase conventions, etc., this is what we would obtain eventually. Now one thing we wanted to do was to see how the differential cross section, which is a function of k, the energy of our incident particle, how it changes with k. Now let's look at two limits. Well, let's look at first of all how this thing behaves. This is nothing but from here we have the sine squared of delta L. This is equal to JL squared Ka divided by JL squared Ka plus YL squared Ka. Now, of course, you can go out and look for the limits of this function, but let's do something else. Have you ever used Mathematica? Well, it's a computer program which you can use in Otto, which knows almost all the functions that you know, and it also knows functions that you don't know. So what we want to have is just look at this ratio. We have the spherical function j over the spherical function j plus spherical function y. Spherical Bessel j, let's call that Ka as a x. So k times a, it doesn't have any dimension. K squared divided by spherical Bessel j Lx squared plus spherical Bessel y Ly squared. So this is our function that we would like to study. Now, one thing you might be interested in is how it behaves at low energies, that is small x. Well, again, Mathematica has some nice features. It can make Taylor expansions. So let me first create a table of these things for various values of L. Let's just check the first 4 values of L, L0 up to 3. And let's make a, or what did I do? This is x. Let's take a series expansion of each one of these terms for x around 0. Let's just take one term. Let's take two terms. Well, you see, for L equal to 0, it starts with x squared. That's the first term. For L is equal to 1, it starts with x to the 6, and x to the 10, x to the 16, etc. So if we are taking, remember, x is k times a. So if you come back over here, so what we have now is sine squared delta L is of the order of Ka to the 4L plus 2. So if you look at the various terms, the order of this ratio increases by 4. For each increase of L, the first contribution increases by x to the power 4. So the only thing that we are interested in will be the L equal to 0. That will be the only one contributing to our cross-section, because we will be taking the limit as k goes to 0. That is the low energy limit. As k goes to 0, if any contribution to sine squared delta L that goes to 0 faster than k squared will be 0. So only L equal to 0 contributes. For k going to 0 limit, and the total cross-section we obtain, it is 4 pi over k squared. Now L equal to 0 term, 12 plus 1 is just 1, and sine squared delta L is just k times a squared. So this is how we obtain 4 pi a squared. So at the low energy scattering, we have the quantum cross-section is larger than the actual cross-section of the object. Now we can study the other limit. Now in the other limit, let's do something different. I mean, we can make a Taylor expansion of this f even for large x, but that is kind of not so illuminating. Let's look at this one. Let's see how these functions look like as a function of x. Let's say from 0 to 20. Yeah. Let's plot it from x is equal to 0 to 20, and we would like to study from L0, let's say, to 20. So this is for L equal to 0. Well, one thing to pay attention to is that it's oscillating. So there are values of energy for which there is no scattering, there is no contribution to the scattering cross-section. This phase shift is 0. So sine squared delta L is 0, as if our object is not there. So this happens when the phase shift is a multiple of 2 pi. So it just becomes invisible for our object at that angular momentum. So this is what happens when you increase L. So it basically shifts. But you see, there's all these regions which doesn't scatter as you increase L. So you see, what we are looking for is the limit. Now we are fixing x maybe to some large value. But then this tells us that as L is increasing, after a value of L for a given x, there is no contribution after a given value of L. There is a contribution to the cross-section only up to some L max.
Is it exactly 0?
Well, there is a tail. It's negligible. Now we can, so basically what this tells us is that we can just limit this summation here. We have this summation for the total cross section. We can limit it up to some L max, not up to infinity, but a finite value of L max. L from 0 to L max of 2L plus 1 times sine squared delta L. Now first let's see, why does this L max come? Where does it come from? Well, if you consider the scattering from the classical perspective, so you see we have in the classical picture, this is our target. We are sending particles of a given energy k and of a given momentum k, wave vector k. And let's say this is B. What is the angular momentum of this object? L is equal to h bar k is the momentum and its mass times B. Well, B can take a maximum, in the classical picture, B can take, if there is a scattering, B can take a maximum value of A, which is less than m h bar k times A. Well, this is basically why we have a maximum limit of the angular momentum. Because if the angular momentum is too big, it just means basically, at least in the classical picture, it is going far away from the, for a given energy. If the angular momentum is large, it just means that my particle is moving very far away from my obstacle, so it doesn't scatter, it doesn't hit it. So this is why we have a maximum value of L. And we can just say that h bar L max should be less than this one. We can cancel h bars. So, yep, there's no m. H bar k is already the moment. So L max is less than k times A. So sigma just becomes 4 pi over k squared sum over L from 0 to an integer a bit less than ka of 2L plus 1 times sine squared delta L. Now you have seen that sine squared delta L is also oscillating. So we can basically replace it by, as an approximation at least, we can just approximate it by its average. So if we just replace it by its average, which is just 1 over 2. Let me put the L max over here.
Are you doing something semi-classical?
Not really. You see, this is our quantum mechanical result here. Then we said that, you see, here, for a given value of k, only up to a finite value of L we receive contribution. For anything above that value of L, we don't receive any contribution to the total cross-section because the phase shift just turns out to be 0. And then what we are saying is, okay, we are using the semi-classical interpretation to understand why we have this maximum L. And then from that semi-classical approximation, we relate that L max to the size of our Hart sphere and its wave vector. This is the semi-classical approximation, in a sense. But we can also remove that approximation. And then we have, if we replace 2L plus 1 times 1 over 2. So this is 2 pi over k squared, sum over L from 0 to some maximum value of 2L plus 1. So what's this value? Does anybody remember?
L plus 1 plus L plus 1 plus L plus. L max artı 2 çarpı
L max, L square plus 2L.
yeah, something like
No, that's it. Yeah, you see, think about the hydrogen atom. For a given value of n, how many states do you have? N squared. And L can take values up to n minus 1. So this is L max plus 1 squared.
Benim dediğim gibi bir şey işte hocam.
But that one we can just ignore it because we are already assuming that we are at high energy. So L max, which is Ka. Well, by the way, the maximum value of L is Ka. So we are already looking at the high energy limit when K is large. When K is large, so L max is large, so 1 we can just ignore it. So this is 2 pi over K squared times Ka squared. K squared A squared, this is equal to 2 pi A squared. Now another thing that you can do is in the summation L, instead of taking L from 0 to, instead of using a summation, you can just integrate it, that summation. If you integrate it, that summation, the result L is equal to 0 to Ka 2L plus 1 sine squared delta L, which if you approximate it by an integral from 0 to infinity of 2L plus 1 sine squared delta L, this just turns out to be approximately Ka squared times 0.6. Well, what we had done is instead of 0.6, we just had 0.5, 1 over 2. So basically, this 2 pi A squared is approximately correct, and we don't even need this semi-classical approximation. So it's just good enough. Any other questions? Okay, so let's go to the Born approximation. Now what we had done up to here, it was kind of a simple example where we could actually explicitly solve it. And what we had seen, I mean, we will come back to this point later on, but if you, okay, so where was it? Okay, basically this was our scattering solution. There is an ingoing, we are sending an ingoing wave, and then it comes out as an outgoing spherical wave. And this F, if you just follow it, the only thing that actually happens is that this ingoing wave becomes an outgoing wave with a phase. There's this phase shift. And in fact, whatever potential you take, that's the only possibility. Because as long as you have a bounded potential over here, your solution has to be of this form, and for a given L, your solution has to look like either as an ingoing wave or an outgoing wave. There's no other alternative to it. The radial dependence at the faraway distance we know, even if we don't know the potential. So the only flexibility we have is that the outgoing wave will acquire an additional phase if there is a potential. So that is the only possibility. There's no other alternative. And that phase shift and that additional phase is what determines the differential cross-section. And in fact, all the properties of the scattering will be determined by those phase shifts. Well, hold on. Before going on with this Born approximation, let's also look at one more thing. Let's look at these two expressions. Now, what is the imaginary part of f at zero scattering? Well, let's just write f in an alternative form, which will make it easier to see. F is equal to minus 1 over k, L from 0 to infinity, 2L plus 1, PL of cosine theta, times e to power I delta L, e to power minus I delta L, plus e to power I delta, no, minus I delta L over 2I. And this is minus 1 over k, or 1 over k, L equal to 0 to infinity, 2L plus 1, PL cosine theta, sine delta L, times e to power I delta L. What is the imaginary part of f? Why? Okay, 2L plus 1 is real, PL is real, sine delta L is real, but there's an exponential over there. It's non-zero. So this is 1 over k. L equal from 0 to infinity, 2L plus 1, PL of cosine theta, sine squared delta L. Well, if it wasn't for this PL of cosine theta, we have the total cross-section. But you see, PL of 0 is 1. So if you take the imaginary part of f at 0 scattering, this is equal to 1 over k, L equal from 0 to infinity of 2L plus 1 sine squared delta L. Well, let's look at the cross-section. It has the same sum, but there's an additional 4 pi over k. So the amplitude for no scattering, or forward scattering, let's say f is by definition the scattering amplitude, but there is no direction, the orientation doesn't change. So the imaginary part of the forward scattering amplitude basically gives us the total cross-section. This is called the optical theorem. Well, there are certainly basic limits on this. For example, let's see, imaginary part of f of 0 is less than the absolute value of f. Which is proportional to, let's say, square root of sigma. Now, these are sometimes called the unitarity bounds. So there are limits on your cross-section which your theory should satisfy. These are things that you should check. Now, if you were following any discussions on the Higgs, people were saying that, oh, it is before the discovery of the Higgs. One of the common things that people used to say is that, okay, if we don't discover Higgs, then the unitarity bound will be violated. So Higgs has to be there. So basically, the amplitude was, for some scattering process, the amplitude of scattering was increasing beyond the total cross-section, which just cannot be. So there had to be something new. Anyway, let's come to the Born approximation. Now the problem let's go back to our initial problem. So what we had in mind was we had such a problem plus V of R psi is equal to E of psi. This is what we wanted to solve. And we wanted to find scattering solutions of this which look like a plane wave plus a spherically outgoing wave. So this was our initial perspective. And if we just identify the spherically outgoing piece, then that gave us the F, or the differential cross-section. Now this V we don't know. Let's just combine the things we already know. And on one side, minus h bar squared over 2m Laplacian minus, instead of E, let's use h bar squared k squared over 2m psi. This is equal to minus V of r psi. Or we can just say that Laplacian plus k squared acting on psi, this is equal to 2m over h bar squared V of r psi. This is our differential equation. Now we can convert this to an integral equation rather than a differential one if we can find the solution of this equation. Let's say Dirac delta r minus r prime. If we can solve this equation, let's say not psi, but g, which will be a function of, also a function of r, it will be a function of r and r prime. If we can solve this equation, then we can say that psi will be equal to psi 0 plus integral d cubed r prime g of r prime 2m over h bar squared v of r prime psi of r prime. And psi 0 being the solution of the homogeneous equation. Well, that psi 0 will be our plane wave. So the first term is kind of our plane wave solution. The second one will be maybe it might also have a plane wave contribution, but plus an outgoing wave. That is what we are looking for. Now, how to see that this satisfies? Well, basically, just place this equation into our differential equation over here. If you apply our operator on psi 0, you get 0. When you act your operator on this g, you get the Dirac delta, using which you can integrate over r prime, and this is what we would get. So the task is kind of just solving for this function g, which is also called the Green's function. Or in this context, we will call it the propagator. Now we can look for a solution of g. Well, g, we can find a solution of g which will be a function of only of the difference. Basically, if you just change r to r plus r prime, the differential equation does not change. The right-hand side depends only on the new r. And so that basically tells you that the Green's function has to depend on the difference on the position, not on any one of them separately. And g now satisfies g of r is equal to Dirac delta of r. Now we can look for the solution of this equation in momentum space. We can just say that, okay, let's define g of r to be d cube p over 2 pi cube e to the power I p dot r. Let's use g, small g of p. And we also know that the Dirac delta we can write in a similar form, d cube p divided by 2 pi cube e to the power I p dot r, and just 1. Now if you just put these equations into our differential equation, we get d cube p over 2 pi cube e to the power I p dot r multiplying minus p squared plus k squared. Well, Laplacian acting on the exponential just gives me minus p squared g of p This should be equal to d cube p over 2 pi cube e to power I p dot r, and g of p is equal to 1 over k squared minus p squared. So this is kind of our solution in Fourier space. So now we can go back to our coordinate space. So g of r is equal to d cube p over 2 pi cube e to power I p dot r over k squared minus p squared. Well, kind of it looks fine for the time being. Let's do some of these integrations. Now we can just assume that in the integral r is just a constant. We can take the direction of r to be our z-axis. So this just becomes p squared dp over 2 pi cube e to power d cosine theta d phi e to power I pr cosine theta divided by k squared minus p squared. Now theta goes from minus 1 to 1 cosine theta. The phi goes from 0 to 2 pi. Nothing depends on phi. So this is equal to 2 pi integral from 0 to infinity p squared dp over 2 pi cube 1 over k squared minus p squared. And cosine theta integral just gives me e to power I pr cosine theta divided by I times pr. Cosine theta goes from minus 1 to plus 1. This is equal to 2 pi over I times r. Well, this is kind of nice because if you remember, this 1 over r was something we were expecting. In our solution, in our general solution, we had this e to power I kr over r. So it seems to be coming. And then integral from 0 to infinity. This p cancels one of the p's over here. And I have the 2 pi cube. And p dp over k squared minus p squared e to power I pr minus e to power minus I pr. Let me just split these two terms into two different integrals. Minus I over 2 pi squared I times r. From 0 to infinity dp p times e to power I pr divided by k squared minus p squared minus from 0 to infinity dp p times e to power minus I pr over k squared minus p squared. Now in the second integral, let's just replace p goes to minus p. So that both integrals will look, the integrands will look similar. 2 pi squared I r from 0 to infinity dp p e to power I pr divided by k squared minus p squared. Okay, from dp I get a minus sign. From p there is an additional minus sign, so there is no sign change. But now the limits are from 0 to minus infinity dp p e to power I pr divided by k squared minus p squared. Now I can change the order of integration. Rather than from 0 to minus infinity, I can take it from minus infinity to 0. That brings an additional sign, so there is a plus sign in between. But then my integrals are from minus infinity to 0, then from 0 to infinity. So that's basically a single integral. If there's no I over here. Minus I over 2 pi squared, or yeah, from minus infinity to infinity dp times p e to power I pr divided by k squared minus p squared. This is my g of r. Now comes the problem. This integral is not defined. You see, as we are integrating over p, when p is equal to k, the integrand diverges. It's not defined. So the integral has two poles. One when p is equal to k, and another one when p is equal to minus k. So that we have to somehow get rid of. You see, this is a solution of our differential equation. But if we add, let's say, well, let me just draw it like this. This is my complex momentum plane P. And I have poles. This is the imaginary part of P. This is the real part. This is the imaginary part of P. And I have a pole over here. This is plus k. And another pole over here. This is minus k. So these poles are what makes my integral diverge. Well, there are a few things we can do. I mean, there are a few approaches. Once we agree that our derivations would have been exactly the same if the integration is from in the complex p plane, from minus infinity to plus infinity, and as long as it goes from minus infinity to plus infinity, we don't really care which path we take. All the paths will give me the same solution. Whichever path I take, I will get a solution of my differential equation. Well, that is one point of view. Another point of view is you can just say, okay, you would like to keep your integral on the real axis in the complex p plane. Then you can just move these poles slightly. You might, for example, just move them above by epsilon. Then they are no longer in your integration path. So your integral is well defined, and you have a solution of the differential equation. Of course, if you move them by epsilon, then what you obtain is a solution of the differential equations with corrections that are proportional to epsilon. It will not be exactly equal to that. But once you shift your poles by epsilon and then take your limit as epsilon goes to 0, what you obtain will be a solution. Now, of course, there is a problem. How do we shift them? Shall we shift them both up or down, one up, one down? So that's kind of the problem. Well, that will be determined by the boundary conditions. You see, we have a second order differential equation. Well, it basically has infinitely many solutions. Infinitely many solutions because we have one homogeneous solution, one particular solution, and we can add any homogeneous solution we like. And basically this ambiguity in the choice of how we shift the poles is just the ambiguity in the choice of the homogeneous solution that we add. But that homogeneous part is we fix by our boundary conditions. Now let's say the general solution. Now I would like to take it as a complex integral. If I want to use the Cauchy's integral formula, I have to consider closed paths. So how should I close my path? From the positive imaginary plane or the negative imaginary plane?
Half a circle.
Yeah, but which one? Should I close it above or below? So my integral is along the real line. This is my integration. I want to add a semicircle at infinity which will not contribute. So that's what I would like to do. I would like to close this loop by a semicircle, either going above the real line or below the real line. But I should add it in such a way that that loop, the integral over that part, gives me 0. So how can we determine that? Let's see. This is our factor, right? This is our integrand. And P, I can just say that P is equal to, let's say, x plus IY on this circle at infinity. X squared plus y squared will be my circle at infinity. The radius squared of the circle at infinity, I can just take that radius to be infinite, eventually. Now, if we use this, let's look at only the exponential part, e to the power I PR. So this becomes e to the power I x times r times e to the power minus y times r. But remember, at infinity, both x and y are infinite. So y should be positive infinite. If y is positive infinite, then e to the power minus I just goes to 0, so I receive no contribution. Now, y being positive infinite just means I'm closing my loop from the above contour, from the above the real line. So this will be my contour now. This is r, this is minus r. Eventually, I would like to take the limit r goes to infinity. Now, depending on how I close my how I shift my poles, one or the other one can contribute. Let's calculate the residues. Now, since I'm integrating over a closed path, dp from minus infinity to plus infinity, p e to the power I pr over k squared minus p squared, this is equal to, now this is an integral over the closed contour, dp p e to the power I pr divided by k squared minus p squared. And I know that this is nothing but 2 pi I times the sum over the residues. Or sum over the poles in my contour of the residue of the pole. I already know where the poles are. Well, I didn't yet decide whether to shift them up or not, up or down, but there are two poles. They can be inside or outside. It will be determined by my boundary conditions. Then I need the residues in my poles. So let's calculate the poles. Do you remember how you calculate the poles? The residues?
There was a formula.
Residue of p times e to the power I pr over k squared minus p squared when p goes to plus or minus k this is equal to the limit. Well, this is a simple pole. Well,
First multiply.
by k minus, no, p minus plus or minus k times p e to the power I pr divided by k minus p, k plus p. I just factorize the denominator, and I'm taking the limit of p goes to plus or minus k. And this is equal to, if I take the lower sign, then above I have p minus k, it cancels this k minus p, bringing me a factor of minus 1. And if I took the lower sign, right? Okay, I took the lower sign, so p goes to plus k, I have 1 over 2k. K e to the power I kr divided by 2k. This is for the lower sign. Now, if I take the above sign, I have p plus k. Now, p plus k, cancel this p plus k. P goes to minus k, so here I have a 2k still. Above, I get, instead of p, I have a minus k. So here this is also plus or a minus k.
But then in the above we don't have an additional minus.
Oh yeah, true. Minus or plus. So for both of them we have a minus e to power plus or minus I k r over 2. This is the residue I have. So G let's see, we had this integral, but then we have this minus I over 2 pi squared r times, from the residue theorem, we have a factor of 2 pi I. And then the sum of the residues just gives me whichever pole I want. This minus 1 over 2 e to power plus or minus I kr. I can take both of them, I can take only one of them, whichever one I want. And because both of those terms are solutions of my differential equation that I'm looking for. Now comes the boundary condition. I want a spherically outgoing wave. This is my boundary condition. And this boundary condition already tells me which residue to put in my contour and which residue to keep out of my contour. So basically, we are keeping the lower sign, we are keeping the lower sign, so I'm just moving this one above, the other one below my contour, so that only this pole contributes. You see, all possible choices of the shifting of the poles is a solution of my differential equation. There's no problem with that. But I also have the boundary condition to satisfy. And that boundary condition fixes my solution. G of r, this is equal to, let's see, this 2 pi cancels one of these 2 pi's. And this minus I cancels this I. And we are left with minus 1 over 4 pi r e to power I k r. This is my Green's function. Or propagator. So now we have our integral equation. So you see, this was our solution. This was the general solution we had. Then we know what this G is. Minus 1 over 4 pi r r minus r prime e to power I k r minus r prime 2m over h bar squared v of r prime psi of r prime psi 0 of r plus or minus m over 8 pi h bar squared d cubed r prime e to power I k r minus r prime divided by r minus r prime p of r prime psi of r prime. Okay, now we need to extract f. Well, let's give a 5-minute break and then we can continue.